our math stat class can be broken down into three main topics. We had point estimation, interval estimation, and hypothesis testing. So we've already covered point estimation and interval estimation, and now we're finally getting into this last topic of hypothesis testing. All right, so we're going to start off by using hypothesis testing to think about one mean. So a few important terms that we should get out of the way. First of all, what is a hypothesis? What is this hypothesis testing stuff? So a hypothesis is just a statement about a population parameter. So if we're doing hypothesis testing for one mean, then we're going to be making hypotheses or statements about this population mean. All right, so there's different kinds of hypotheses. We could have a simple hypothesis or a composite hypothesis. So if we have something like the hypothesis mu equals 10, that's just a simple hypothesis because we're saying the parameter is equal to a single point. Then if we have a composite hypothesis, then we're saying that the parameter is in an interval. So maybe our composite hypothesis would be something like mu is greater than 10. All right, so in this first example, we're going to think about just two simple hypotheses. So we have some distribution. It's a normal distribution with unknown mean mu and variance 36. So sigma squared equals 36. And perhaps someone told us that mu is equal either to 50 or 55. So perhaps we set up our hypotheses like the null is the simple hypothesis mu equals 50, and then the alternative is the simple hypothesis mu equals 55. So for some reason, we have reason to believe that mu is equal to 50, but if we have enough evidence, we're going to reject this null hypothesis in favor of the alternative hypothesis that mu is equal to 55. All right, so how do we actually decide whether to reject the null hypothesis or not? So we're going to form some kind of rule, and that rule will tell us whether or not to reject the null. So perhaps this is our rule. If the set x1 through xn is in some interval C, we're going to reject the null in favor of the alternative. And if the set x1 through xn is in C prime, then we will not reject the null hypothesis. So what we've done is we've taken our sample space for x1 through xn and partitioned it into two pieces, C and C prime. So C and C prime, the union of them gives us the entire sample space, and these two, C and C prime, do not overlap at all. All right, so we've partitioned our sample space into C and C prime, and then we're saying if x1 through xn lands in C, we will reject the null, and if x1 through xn lands in C prime, we will not reject the null. Okay, so what might C and C prime look like? Well, lots of times we take our sample x1 through xn and create a test statistic. So maybe our test statistic, since we're talking about one mean, one population mean, our test statistic would be the sample mean x bar. So maybe C would be the set of all x1 through xn such that x bar is greater than or equal to 53, and C prime would be the set of all x1 through xn such that x bar is less than 53. So what this is saying is if our sample lands in C, in other words, if we have x bar greater than or equal to 53, we're going to reject the null in favor of the alternative. So that kind of makes sense. What's our null? It's mu equals 50, and our alternative is mu equals 55. So this is saying if our sample mean is big enough, greater than or equal to 53, then we're going to reject the null, mu equals 50, in favor of the alternative, mu equals 55. And then C prime is the set of all x1 through xn such that x bar is less than or equal to 53. So what this is saying is if our sample mean is less than 53, then that means we've landed in C prime and we will not reject the null. So if we have a small enough sample mean, then we're going to not reject the null hypothesis that mu equals 50. In our previous video on hypothesis testing, we learned that at the end of a test, we end up either rejecting the null hypothesis or not rejecting the null hypothesis. So there's two decisions we could have made, reject or not reject. In the real world, there's some unknown truth, and it's either that the null hypothesis is correct or that the null hypothesis is incorrect, meaning that the alternative is incorrect. All right, so if we put this into a little matrix, here's the unknown truth. The null is correct or the alternative is correct. And then remember, there's two decisions we could have made. We could have rejected the null or not rejected the null. So if the null was actually correct and we did not reject it, then that's a good thing. We did not make any sort of error. Similarly, if the alternative is correct and we did reject the null, that's another good thing. We did not make an error. So the error comes in on the diagonal here. So if the alternative is correct, but we do not reject the null, then that's called a type 2 error. Similarly, if the null is correct and we end up rejecting the null, that's called a type 1 error. All right, so those are just some definitions. Type 1 error is just rejecting the null when it is actually correct. The type 2 error is not rejecting the null when the alternative is correct. Okay, so how often do these errors happen? Well, we can call something the significance level and define that alpha, and that is the probability that a type 1 error happens. So in other words, the probability that we will reject the null, even though in reality the null is correct, is what we call alpha, the significance level, and then the probability of committing a type 2 error is what we're going to call beta, and later we'll talk about how 1 minus beta is the power of a test. Okay, so we can see we have these different two types of errors, type 1 error and type 2 error. All right, so let's see how often these happen. Let's check out the alpha and beta in a specific example. So from the last video, we're going to continue on with that example there. And we had the decision rule from the last video that we're going to reject the null hypothesis if our sample mean is greater than 53, and we will not reject the null hypothesis if our sample mean is less than 53. All right, so again, just remember we had a normal distribution, known variance 36, unknown mean of mu. And we said our null hypothesis is mu equals 50, alternative hypothesis is mu equals 55. So let's say that we go out and take a sample of size n equals 16. All right, so we're trying to figure out if we have a sample of size n equals 16, what's the probability that we will mistakenly reject the null hypothesis? Similarly, if we have a sample size of n equals 16, what's the probability that we will mistakenly not reject the null hypothesis? So those are alpha and beta respectively. Okay, so first let's start with alpha, the probability of a type 1 error. In other words, the probability of mistakenly rejecting the null. The probability of rejecting the null given that the null is actually true. Okay, so this is just the very general definition of alpha. Let's plug in what our null hypothesis is in our case. So in our case, our null hypothesis is mu equals 50. So we go ahead and plug that in there. So we have the probability of rejecting the null given mu equals 50. But we have that decision rule, so we can also write, instead of reject null, we can write what our decision rule is. Our decision rule said reject if x bar is greater than or equal to 53. So we can go ahead and write that here. The probability that x bar is greater than or equal to 53, given that in reality mu equals 50. That's what our significance level alpha is. All right, but we can take this further. We can actually crank this down to a single number. So if we go ahead and define a random variable, z, that is standard normal. So let's go ahead and subtract and divide by the same quantity here on both sides. So if we subtract 50 from both sides and then divide by the standard error of x bar, in other words, we have the square root of 36 divided by the square root of the sample size 16. So in the denominator we've divided by 6 over 4 on both sides. All right, so we've just done the same manipulation to both sides, to both x bar and 53, so we have the probability that x bar minus 50 divided by 6 over 4 is greater than 53 minus 50 divided by 6 over 4, given that in reality mu equals 50. Okay, but this is actually a standard normal random variable because we've subtracted off the mean, which in reality was 50, and we've divided by the standard error of x bar. So this is actually just a standard normal random variable, which we called z. So now this is equal to the probability that z is greater than or equal to 53 minus 50 divided by 6 over 4. All right, so this is just equal to 2. So our probability of committing a type 1 error is just the probability that a standard normal random variable is greater than or equal to 2. All right. So here's our standard normal random variable. Here's 2. And that area shaded there is just the probability of committing a type 1 error. So we can go to a table, or we could use p norm and r to figure out that this area is 0.0228. Okay, so what does this all tell us? This tells us that if in reality the null is true, meaning mu truly is 50, if we take a sample of size n equals 16, then about 2.28% of the time we're going to mistakenly reject the null hypothesis. So in other words, imagine taking a sample of size 16 and then deciding, do we reject or do we not reject based on this rule? And then we do that again. We take another sample of size 16 and decide, do we reject or do we not reject based on this rule? We do that over and over and over and over and over, maybe a million times. Then about 2.28% of the time, we're going to end up mistakenly rejecting the null hypothesis. All right, so that's our probability of a type 1 error, the probability of mistakenly rejecting that null hypothesis. All right, how about beta, which is the probability of a type 2 error, or in other words, the probability of mistakenly not rejecting the null hypothesis? Well, we can calculate beta in a similar way. First, let's just start with the definition of beta. So beta is the probability that we do not reject the null, given that the null is actually incorrect. Okay, but what does it mean to not reject the null? Look at our decision rule. We will not reject the null if x bar is less than 53. So let's swap out this statement, do not reject the null, for our actual rule, x bar is greater than 53. Similarly, we can swap out the statement h naught is incorrect, or the null is incorrect, with what that actually means in the context of our problem here. So if the null is incorrect, then the alternative is correct, meaning mu equals 55. Okay, so we can swap out the statement the null is incorrect for the statement mu equals 55. All right, so our beta, our probability of a type 2 error we figured out so far, is the probability of seeing a sample mean less than 53, given that in reality mu is equal to 55. Okay, so it should make sense that sometimes, even if the mean truly is 55, we know there's variability in those x bars, so sometimes we're going to end up getting a low sample mean, maybe lower than 53. Okay, so let's continue thinking about this. Let's do the same thing as here and subtract and divide by the same quantity. All right, so let's subtract by 55 on both sides and then divide by the standard error of x bar. So subtract off 55 on each side and then divide by 6 over 4. Again, 6 is the square root of 36, and then 4 is the square root of our sample size 16. All right, so then that tells us that beta equals the probability that x bar minus 55 over 6 over 4 is less than 53 minus 55 over 6 over 4, given that in reality mu equals 55. So again, this quantity here is a standard normal random variable, right? Because we know that x bar has a normal distribution with mean 55 and then variability 36 over 16. So we've subtracted off the mean divided by the standard error, which is just the square root of 36 over 16. So this is just a standard normal random variable. And this is just a number. It ends up equaling -4 over 3. All right, so that means that the probability of mistakenly not rejecting the null hypothesis when we have a sample size of 16 is equal to the probability that a standard normal random variable is less than -4/3. So maybe that's like here. So this is our beta type 2 error. So again, this is a standard normal random variable, so we can go to our table or we can use pnorm in R to figure out that this probability is 0.0913. Okay, so again, what does this mean? So imagine that the null is actually incorrect. So in reality, actually mu is equal to 55. So the truth out there is mu equals 55. Now imagine you take a sample of size 16 from this distribution. You calculate its sample mean, and then based on that you decide, okay, reject the null or do not reject the null. Then you get another sample of size 16, follow the same process, end up rejecting or do not rejecting. You do this over and over and over for some huge number of times, maybe 1 million, maybe 10 million, and then what you'll find is that about 9.13% of the time you will be mistakenly not rejecting the null. So the correct thing to do would be to reject the null, but 9.13% of the time you will end up not rejecting the null, and that's incorrect because in reality the null is not true. The alternative is true. All right, so that's a little example for our probability of a type 1 error here, and then our probability of a type 2 error there. So something to note is that we can only know what decision we're making. When we do a hypothesis test, we know whether we end up rejecting the null or whether we end up not rejecting the null. Of course, we don't know the truth. We don't know whether the null is actually correct or whether the alternative is actually correct. If we did, then why would we be doing hypothesis testing at all, right? So all we can do is try to make this decision to reject the null or not reject the null. So since we only know whether or not we're rejecting, and we do not know whether or not the null is incorrect or correct, then we don't know when exactly we're making a type 1 error, and we do not know exactly similarly when we're making a type 2 error. So all we know is that as statisticians going through our life, we're going to be doing lots of hypothesis tests. And what we know is that some of the time we're going to be making a type 1 error, and some of the time we're going to be making a type 2 error. We'll never know when exactly, we just know that this is bound to happen. So a good thing to know, since we know that this will definitely happen sometimes, a good thing to know would be how often are we going to be committing this type 1 error? And how often are we going to be committing this type 2 error? Okay, so something also to say is that error doesn't mean that we as statisticians did anything wrong. We could have crunched all the numbers correctly. We could have gotten perfectly a random sample. We could have done every single step correctly. And then just by random chance, we could have ended up with a sample mean that is greater than 53, or we could have ended up with a sample mean that is less than 53 just by random chance, because we know that there's always going to be that variability in our sample means. So it doesn't mean we did anything wrong when we say type 1 or type 2 error. This is just something that happens because we're statisticians and we're doing hypothesis testing. There's no way that we can avoid type 1 or type 2 errors. All right, in previous videos we've talked about hypothesis testing and how it ends up where we either reject the null hypothesis in favor of the alternative or we don't reject the null hypothesis. So how do we end up deciding whether or not to reject the null hypothesis? So we said we had some decision rule, and that decision rule would say, okay, if blank, then we reject the null. If blank, do not reject the null. But we're going to talk a little bit more in detail about that decision rule there. Okay, so first, a couple definitions. We have test statistic. Okay, so we know a statistic is a number based on a sample, right? So a test statistic is a function of the sample, and because it's a test statistic, then we know that we're going to use that statistic to conduct our hypothesis test. So, for example, if we're working on hypothesis testing for one population mean, then we might use a test statistic of our sample mean. Okay, so there's our test statistic. Then we use our test statistic to calculate what's called a p-value. So the p-value is the probability of getting a test statistic as extreme or more extreme than the one that we observed based on our sample, assuming that the null hypothesis is true. Okay, so in this p-value, it's all given that the null hypothesis is true. So we're assuming the null hypothesis is true, and then we're calculating the probability of getting a test statistic as extreme or more extreme than the one that we observed based on our sample. Okay, so we're assuming that the null hypothesis is true in our p-value because in the hypothesis testing framework, we assume the null is true until we have evidence otherwise. All right, so there's our definition of p-value, but how do we actually use them? So p-values measure the evidence against the null hypothesis. So if we have a lot of evidence against the null hypothesis, that means that we're going to have a smaller p-value. Because if we think about it, our test statistic is going to be very extreme when we have a lot of evidence against the null hypothesis. So if we have maybe here's our sampling distribution for the test statistic. If we go further and further into this tail to calculate our p-value, the shaded area there is our p-value. As we go further and further into the tail, then we're going to be shading a smaller and smaller area, and so our p-value is going to be getting smaller and smaller as we get more and more evidence against the null hypothesis. So when we see a small p-value, then we know that we're going to want to reject the null hypothesis. So we calculate their p-value based on our test statistic, and then we will end up rejecting the null hypothesis if our p-value is small enough, so smaller than some predetermined threshold. So from applied stats classes, you probably know that that threshold is called their significance level, and so if our p-value is smaller than that predetermined significance level alpha, then we're going to reject the null hypothesis. All right, so let's see an example of calculating this p-value. So in this example, we have a normal distribution, mean mu, variance sigma squared. Mu is unknown because we're doing hypothesis testing for a mean, and assume that sigma squared is known and it's equal to 100. All right, so our null hypothesis perhaps is mu equals 60, and the alternative is the composite hypothesis, mu is greater than 60. So remember, simple and composite hypothesis. A simple hypothesis is like our null hypothesis here. Our parameter is just equal to a point. And then the composite hypothesis is saying something like mu is greater than 60. It's giving an interval for what mu is in. Okay, so we want to test these hypotheses. Mu is equal to 60 versus the alternative mu is greater than 60. And so we go out and collect a sample of size 52, and we calculate the test statistic x bar, the sample mean, and it ends up being 62.75. All right, so with that information, we want to calculate our p-value. All right, so remember our p-value is the probability of getting a test statistic as extreme or more extreme than the one that we observed from our sample, given that the null hypothesis is true. So when we're calculating our p-value here, we're assuming that the null hypothesis is true. So we're assuming that mu equals 60. And then we're saying, what is the probability of getting a test statistic x bar as extreme or more extreme than 62.75, given that mu is actually equal to 60? All right, so we have our normal distribution with mean 60 under the null, and then variance sigma squared equals 100. So under the null hypothesis, we have this normal distribution here with mean 60 and then sigma squared 100. Okay, so we go out, collect our sample of size 52, and we get a sample mean of 62.75. And then we're wondering, what's the probability of getting a test statistic, x bar, as extreme as 62.75 or more extreme? So extremeness would be moving further away from our null hypothesis value. So this shaded area here, that's our p-value. That's the probability of getting a test statistic as extreme as 62.75 or more extreme than 62.75, given that the null hypothesis is true. In other words, given that mu is actually equal to 60. All right, so that's our picture here. This is the area that we're looking for. So we can continue on to calculate that number here. Okay, so here's our setup, but we know that x bar has a sampling distribution under the null hypothesis that is a normal distribution with mean 60 and then variance 100 divided by 52. So remember, if our distribution for x had variance sigma squared, then we know that the variability for x bar is going to be sigma squared divided by our sample size. So sigma squared 100 and then sample size of 52. Okay, so we have our sampling distribution for x bar. We can go ahead and use that. So we're going to, for both these things, subtract off the mean, which is 60 under the null hypothesis, and then divide by the standard error, which is the square root of 100 over 52. All right, so if we do that, then that tells us that our p-value equals the probability that x bar minus 60 divided by 10 over root 52 is greater than or equal to our observed sample mean 62.75 minus 60 divided by 10 over the root of 52. Given that in reality mu is equal to 60. So again, given that the null hypothesis mu equals 60 is true. Okay, so if we're working under the assumption that mu equals 60 is true, then we know that this is the same thing as a standard normal random variable. Okay, so if we denote our standard normal random variable by z, then this p-value is equal to the probability that a standard normal random variable is greater than or equal to this same quantity, 62.75 minus 60 over 10 divided by root 52. All right, so then we can go to our table or p-norm, and we can calculate our p-value is 0.0237. So this shaded area here, which we said is our p-value, is 0.0237. All right, so when we're calculating these hypotheses, it helps to go back to just the basic definitions. We need to know what is our test statistic that we're working with. Here in this example, our test statistic is our sample mean. And then we also need to know what is the sampling distribution of our sample mean. So here our sampling distribution was a normal distribution with mean 60 and then variance 100 over 52. So that's the sampling distribution of our sample mean under the null hypothesis. Because remember, we have to assume the null is true until we have evidence otherwise. All right, so we've got our sample mean, we've got our sampling distribution for the sample mean, and then we have our sample size and the test statistic that we've observed from that sample of size 52. So then we know that our p-value is the probability of getting a test statistic as extreme or more extreme than the one that we got from our particular sample, given that the null hypothesis is true. So then we can work with that, change that sentence into equations, and then eventually crank it down to a single number like 0.0237. So again, the smaller the p-value is, the more evidence we have against the null hypothesis. In other words, the smaller the p-value is, the more inclined we are to reject the null hypothesis. So if we saw a big p-value like 0.5, we would probably not reject the null hypothesis. And if we saw a small p-value like 0.0237 maybe, or like 0.000001, then we would want to reject the null hypothesis. And we'll end up making that decision rule based on our predetermined significance level alpha. So if our p-value ends up being smaller than alpha, then we're going to end up rejecting the null. And if it's not, then we do not reject the null. right, let's talk a little bit more about p-values. So in the last video, we defined p-value. We said that the p-value is the probability of getting a test statistic as extreme or more extreme than the one that we have calculated based on our sample, given that the null hypothesis is true. So remember, the p-value is saying, all right, assume the null hypothesis is true. What's the probability of getting a test statistic as extreme or more extreme than the one that we have gotten based on our sample data? All right, in the previous video, we calculated a p-value based on the hypothesis, the alternative hypothesis, mu is greater than 60. So how did we calculate that p-value? Well, we said we would need to calculate the probability of getting a test statistic as extreme or more extreme than the one that we got, which was 62.75, given that the null hypothesis is true, meaning given that mu is equal to 60. All right, so here's our null hypothesis, mu equals 60. Alternative hypothesis was mu is greater than 60. So if we wanted to draw a little picture of this, we could draw out our sampling distribution of x bar under the null hypothesis. So that would mean that we draw out a normal distribution with mean 60, because that's what the mean is under the null hypothesis. And then we would make sure that it would have variance sigma squared over root n. Sorry, sigma squared over n. Okay, so here's our normal distribution. It's centered at 60, and then we drew in our test statistic, x bar, which was 62.75. So then, in order to figure out which part to shade, we looked at our alternative hypothesis. So our alternative hypothesis is mu is greater than 60. So we're going to shade everything greater than our test statistic, because this is the direction of getting more extreme. So getting larger and larger x bars means we're getting more and more extreme x bars. So we've shaded our area to the right of our test statistic, 62.75. So again, we shade that right area there when our alternative is saying our parameter is greater than some value. Okay, how about if our alternative hypothesis is our parameter is less than some value? So let's think about if we had our null was 60, and then our alternative was mu is less than 60. So again, we draw out the same picture, or a similar picture. We draw out a normal distribution with the mean given by the null hypothesis. And so this is our sampling distribution of x bar under the null hypothesis. So it's still the sampling distribution of x bar under the null hypothesis. Then say that we took a sample and we got x bar equals 58.1. We would draw in 58.1, and then our p-value would be the probability of getting a test statistic as extreme or more extreme than 58.1 under the null hypothesis that mu equals 60. So if we're trying to look at the probability of getting different test statistics, then we know that those probabilities are going to be given by that sampling distribution for x bar. So here's our sampling distribution for our test statistic under the null hypothesis. Here's the particular test statistic that we got based on our sample. And so we look at our alternative hypothesis to figure out which way is more extreme. So if our alternative here is mu is less than 60, then we know that getting smaller and smaller x bars is going to be more and more extreme. So we draw in 58.1, and any x bar less than 58.1 is more extreme than 58.1. So our p-value is that area shaded there. So that is the probability of getting a sample mean that is as extreme as 58.1 or more extreme than 58.1. Okay, so if our alternative is parameter is greater than some value, shade the area to the right. If the alternative is parameter is less than some value, shade the area to the left. How about if we have what's called a two-sided alternative, meaning in this example here we'd have mu is not equal to 60. All right, so similarly, draw in our sampling distribution for x bar under the null hypothesis. So we know our sampling distribution for x bar under the null hypothesis is the same old normal distribution centered at 60, and then with the variability, with the variance sigma squared over n. Okay, so we've drawn this here, and say we get a test statistic of 58.1. All right, so we draw in 58.1. So if we looked at the lower tail here, in other words, if we look at the probability of getting a test statistic less than or equal to 58.1, that's only half the story, because our alternative is mu is not equal to 60. So we have a two-tailed alternative. So this area here is not our p-value yet. It's only half our p-value. So what we could do is calculate that shaded area there. We could calculate that probability and just double it to get our p-value. So when we have a two-tailed alternative, we need to calculate the area of one tail and then double it. Another way to think about this is draw in our same old sampling distribution for the test statistic under the null hypothesis. So again, normal distribution centered at 60 with the correct variance. Here's our sample mean, 58.1. All right, if we shade the area to the left, then that's saying here's the probability of getting a test statistic that's less than or equal to 58.1. But this 58.1, our sample mean could have just as easily been extreme in the other direction. So since 58.1 is 1.9 away from the mean, let's go 1.9 above the mean as well. So we draw in 61.9. So now we have 58.1, 61.9. These two are equidistant from 60. And so we can shade in that upper area there. So our p-value in this case that we have, the alternative mu is not equal to 60. Our p-value is going to be the sum of these two shaded areas. So it's going to be the probability of getting a sample mean less than or equal to 58.1 plus the probability of getting a sample mean greater than or equal to 61.9. All right, so again, we can have three different types of three different alternative hypotheses. We could have parameter is greater than some value, we could have parameter less than some value, or parameter is just not equal to some value. And so we have to pay attention to what our alternative hypothesis is, because that defines how we calculate our p-value. Previously, we were doing hypothesis testing for a population mean when sigma squared was known. So when sigma squared was known, then we could say that our test statistic was x bar, and then we would wonder what is our sampling distribution for that test statistic under the null hypothesis. So we figured out that the sampling distribution would be a normal with mean mu, variance sigma squared over n under the null hypothesis, where mu was given by the null hypothesis. Okay, so this would be the same thing as, we would get the same results as if we had a test statistic of x bar minus mu under the null divided by sigma over root n. So in other words, we could have had a test stat of x bar with this sampling distribution, or we could have had a test statistic of x bar minus mu over sigma over root n. And its sampling distribution would have been a standard normal distribution. So either way, we would have gotten the same results. In other words, we would get identical p-values whether we had x bar as our test statistic or whether we had x bar minus mu over sigma over root n. All right, so this again was all when we had sigma squared being known. But of course, most of the time, if we don't know the mean, then we won't know the variability either. So it's useful to think about how do we do hypothesis testing when we do not know the variance sigma squared. So hopefully this reminds you of when we did confidence intervals for a mean when we did not know sigma squared. So remember from those videos we said that if we had a random sample of size n from a normal distribution with mean mu, variance sigma squared, with both mu and sigma squared being unknown, then our sample mean minus our population mean divided by s over root n would have a t distribution with n minus 1 degrees of freedom. All right, so we are going to use this when we talk about hypothesis testing for a mean when sigma squared is unknown. Okay, so let's go ahead and talk about that. So we're assuming sigma squared is unknown, then a test statistic that we could use, instead of using this test statistic, which we could use when sigma was known, instead of using this test statistic, let's go ahead and use this test statistic. Okay, so if our null hypothesis is mu is equal to some value mu naught, so like mu naught could be like 60 or something like that, then our test statistic is going to be our sample mean minus the value of mu under the null hypothesis divided by s over root n. So we subtract off the value of mu under the null hypothesis because we assume that mu is equal to mu naught. In other words, we assume that the null hypothesis is true until we have evidence otherwise. So then we have our test statistic that's here, and then we need to know what is the sampling distribution of our test statistic under the null hypothesis. And this tells us that our sampling distribution for the test statistic under the null is going to be a t-distribution with n-1 degrees of freedom. All right, so hopefully you see where this is coming from. Before we had a test statistic of x bar minus mu over sigma over root n, and its sampling distribution was a standard normal. Now we're talking about mu being unknown, so we use x bar minus mu under the null divided by sample standard deviation over root n, and that has a t-distribution under the null hypothesis with n-1 degrees of freedom. Okay, so let's go ahead and do a hypothesis testing example where both mu is unknown and sigma squared is unknown. Okay, so I just made this up, but maybe we could say that Pizza Hut claims that each slice of pepperoni pizza has, on average, 4 slices of pepperoni. And maybe you eat a lot of pizza and you're wondering, okay, is this actually true? Are there really 4 pieces of pepperoni on each slice on average? All right, so then the null hypothesis would be what Pizza Hut claims. Mu, which is the mean number of slices of pepperoni on a slice of pizza, is equal to 4. And then the alternative would be mu is not equal to 4. So if we're just testing, are there actually 4 slices of pepperoni on each slice of pizza, then our alternative would be this two-sided one. Mu is not equal to 4. If you were thinking like they put too few slices of pepperoni on, then you would change this not equal to sign to a less than sign. All right, so we have our hypotheses. Mu naught here is 4. So say that you go out and you randomly sample 9 slices of pizza, so n equals 9, and then you calculate x bar, and you find it is 4.3 slices of pepperoni, and our sample standard deviation is 1.2 slices of pepperoni. So then we can go ahead, plug all those numbers into this form for our test statistic here. So x bar was 4.3, so plug that in. The value of mu under the null hypothesis is 4, so plug that in. S was 1.2, and then n was 9, because we had 9 slices of pizza that we sampled. All right, so our test statistic then is equal to 0.75. All right, so we have our test statistic that we get from our particular sample, and we want to calculate the probability of getting a test statistic as extreme or more extreme than 0.75, given that the null hypothesis is true. In other words, given that the average number of slices of pepperoni on a slice of pizza is equal to 4. Okay, so we need to know the sampling distribution of our test statistic. So here's our test statistic, and we know that the sampling distribution is a t-distribution with n-1 degrees of freedom. So we have 8 degrees of freedom here under the null hypothesis. All right, so let's draw out, here's our sampling distribution. It's a t-distribution with 8 degrees of freedom. This is centered at 0. And then let's draw in our test statistic, which is 0.75. All right, so we know that this shaded area here is half of our p-value, because remember we have a two-sided alternative, so that shaded area is just half our p-value. So we need to find that area, double it, and that's our p-value. Okay, so we can go ahead and calculate our p-value. Our p-value, we said, is just going to be double this area. So it's 2 times the probability that a t-distribution with 8 degrees of freedom is greater than our test statistic, which is 0.75. So then we can go out and use a table, or we could use PT in the PT and R to find out that our p-value is 0.4747. All right, so it looks like because we have a pretty big p-value, we don't have very much evidence against the null hypothesis. So in most settings, we would not be rejecting the null hypothesis here. So in other words, we did not find evidence that the mean number of pepperonis on a slice of pizza is something different than 4. So we'll just go ahead and say, okay, we don't have evidence to reject the null hypothesis, so we'll just keep living in this world that says mu equals 4. In other words, the mean number of pepperonis on a slice of pizza is 4. In the previous videos, we've been talking about having like one variable. So maybe that one variable was the number of slices of pepperoni on a piece of pizza or something like that. In the real world, it's not unusual to see some paired data, so like before and after or something like that. So imagine we have something like a test of some kind, and perhaps before getting trained or before some like class, then we observe these test scores. So maybe Alice got a score of 80, Bob got a score of 70, Carlos 75, Danielle 78, and all the way down to Xander, who got a score of 72. So they took the test, got these scores, and then maybe they had some training, some kind of class or something like that, and then they retook the test and got these new scores. So 90, 91, 90, 98, 92. So if the class works, then we would see an increase. So in other words, if the class works, if the class is effective, the scores after the class should be better than the scores before the class. So what we could do is calculate each person's increase. So like Alice before was 80, after is 90, so her increase is 10. Bob's increase was 21. Carlos's increase was 15. Danielle's increase was 20. Xander's increase was 20. So now we have this new variable, which is just the increase or the improvement in their test score. And we can focus just on this one variable and pretty much forget about these other two variables and do all of our inference on just this one variable there, the increase or the improvement in the test score. So we can do this subtraction here because we have paired data. Alice is paired with herself. Her before score is paired with her after score. Bob's before score is paired with his after score, and so on. So all we're interested in is essentially the difference there. So we can just focus on that improvement or that increase. So now we could go ahead and do a hypothesis test using just that variable there. So we could do something like if we wanted to see whether there was an improvement, the null hypothesis would be there's no improvement, meaning mu is equal to 0, meaning the mean increase is 0. And then if there is improvement, then mu is going to be greater than 0. So we could go ahead and do that hypothesis test. If we have n equals 26 people, then we could calculate x bar, and we could calculate the sample standard deviation. So then our test statistic would be x bar minus mu under the null divided by s over root n. But mu under the null is just 0, so this is x bar over s divided by root n. So we could go ahead, plug in those values, and we know that our test stat follows a t-distribution with n minus 1 degrees of freedom. So since we had 26 students here, we have 25 degrees of freedom. So then our p-value would be 2 times the probability of, actually let's just take out the 2. Our p-value is going to be the probability of seeing an absolute value of a test statistic greater than or equal to our particular test statistic, x bar over s over root n. So again, since we have so since the alternative actually is mu is greater than 0, we're just going to look at the probability that our test statistic is greater than or equal to our particular test statistic. So here's our t-distribution with 8 degrees of freedom. It's centered at 0. We would draw in our particular test statistic, x bar over s over root n. And then our p-value would be that area there. So we're just shading that upper area because our alternative hypothesis is mu is greater than 0. So we would look at the area above our particular test statistic. So there would be our p-value. Okay, so we can see that if we want to do a hypothesis test and we have paired data, let's just use this new variable that we've created, which is just the difference between those two variables. And similarly, if we wanted, we could create a confidence interval for the increase in test score. So it's just going to be our sample mean increase plus or minus our special value of t times s over root n. So remember, we calculate this particular value, t star, using a t-distribution with n minus 1 degrees of freedom. And if we want to have a 1 minus alpha level of confidence, then that means that we have alpha over 2 in each tail. And so then we would look for this value t star such that we'll get alpha over 2 in each tail. So in other words, when we have paired data, go ahead and just find the difference, and that will be what you use to do a confidence interval or a hypothesis test. All right, so you do not want to just ignore the increase and ignore the pairing of the data. If we just kept this as before and after and then ignored that they were from the same person, we would be losing a lot of information. So we don't want to throw away the paired nature of the data because that loses information. It will lose power. It will lose exactness in the confidence interval. So we want to take into account the paired nature of the data by just looking at the difference between the columns. Previously, we talked about hypothesis testing for a single mean, and now we're going to move into comparing two means via hypothesis test. All right, so we know that when we were doing a single mean, we needed to come up with some test statistic, and then we needed to know the sampling distribution of that test statistic. So the same thing's going to apply here. We're going to need to come up with a test statistic, and then we're going to need to figure out what the sampling distribution is for that test statistic. All right, so let's kind of set things up. So first, if we have two means, then that means that we're going to be sampling from two distributions. So suppose we have two distributions. One's a normal distribution with mean mu x and variance sigma squared x. And the other one's a normal distribution with mean mu y and sigma squared mu y as its variance. Okay, so let's take a random sample of size n from the first distribution, and then independently take a random sample of size m from the second distribution. All right, so we know that x bar is going to have a normal distribution with the same mean mu x, and of course the variability, the variance of x bar is going to be sigma squared x divided by n. Okay, so that's basic information. We have known that from probability. Similar thing is y bar is going to have a normal distribution with mean mu y, and then variance sigma squared y divided by its sample size m. All right, so we know this distribution of x bar. We know the distribution of y bar, and we know that x bar and y bar are independent. So we can figure out pretty easily the distribution of x bar minus y bar. All right, so x bar is normal, y bar is normal. If we have a normal plus a normal, we end up with a normal. Okay, so x bar minus y bar is going to be normally distributed. Now we just need to figure out the mean of x bar minus y bar and the variance of x bar minus y bar. All right, the mean of x bar minus y bar. Let's do that first. Expectation of x bar minus y bar, let's use the linearity of expectation. We end up with x bar, the expectation, minus expectation of y bar. So this is just mu x minus mu y. All right, now let's do the variance of x bar minus y bar. And here is where it's going to be useful that we took these two samples independently. Because the variance of x bar minus y bar is just going to be the variance of x bar plus the variance of y bar. And then we don't have a covariance term because we took x bar and y bar independently. So we know that the variance of x bar minus y bar is going to be the variance of x bar, which is sigma squared x divided by n, plus the variance of y bar, which is sigma squared y divided by m. So putting this all together, we know that x bar minus y bar is normally distributed. It has mean mu x minus mu y, and its variance is sigma squared x over n plus sigma squared y over m. All right, and of course, if we wanted to standardize this, we could do x bar minus y bar minus its mean divided by its variance, the square root of its variance. And that would give us a standard normal distribution. So we have a sampling distribution for x bar minus y bar, and this will come in useful when we do our hypothesis testing. Okay, so suppose that we want to test the hypothesis of, are these two means equal? In other words, we want to know, is mu x equal to mu y? So what our hypothesis is going to be, what our null hypothesis is going to be, is the two means are equal, or equivalently, we could write it mu x minus mu y equals 0. And of course, we need to specify our alternative as well. And we know that we could have three different alternatives. We could have the two means are not equal. We could have one mean being greater than the other mean. Or we could have it the other way around, where the other mean is greater than the other mean. So the two means are not equal. Mu x is greater than mu y, or we could have mu x is less than mu y. So choose one of these to be our alternative hypothesis. So regardless of what the alternative hypothesis is, we need a test statistic. And what we would really like is if we could use this test statistic here, because we know its sampling distribution standard normal. So let's go ahead and rewrite this, but take into account the fact that our null hypothesis is mu x minus mu y equals 0. So we copy this down, we get x bar minus y bar, and then this term in parentheses is just going to be 0 because under the null, the two means are equal. And then we have our denominator, which is the square root of sigma squared x over n plus sigma squared y over m. So if we knew sigma squared x and sigma squared y, then we could go ahead and use this test statistic, and we would know this test statistic has a standard normal sampling distribution. But as we know, usually variance is not known. So if we don't know sigma squared x and sigma squared y, what are we supposed to do? Well, a logical thing to do would be use the sample variance. So the easiest thing to do is if we assume these two variances are equal. We'll assume sigma squared x is equal to sigma squared y. Then we can just calculate what's called a pooled sample standard deviation. So to get the pooled sample standard deviation, we're going to take the sample variance of x, multiply it by n minus 1, and then add to it the sample variance of y, multiply it by m minus 1, and then divide by the total sample size. So total sample size minus 2. So we have the sample size of x plus the sample size of the y's minus 2. So this whole quantity there, that's what we're going to call our pooled sample standard deviation. Okay, so it's pooled because we've pooled all the information from x and information from y and come up with one sample standard deviation under the assumption that the variances of the x's are equal to the variance of the y's. All right, so we have our pooled sample standard deviation, and we're going to use that in place of sigma squared x here and sigma squared y here. So if we plug in our pooled sample standard deviation, then we can recalculate this to be just x bar minus y bar minus 0 divided by the pooled sample standard deviation times the root of 1 over n plus 1 over m. All right, so this is the test statistic that we're going to be using. And what is its sampling distribution? It's going to have a t distribution with n plus m minus 2 degrees of freedom. All right, so the sample size of the x's plus the sample size of the y's minus 2. That's going to be the number of degrees of freedom on our on our sampling distribution. All right, so this is what we're going to use. We're going to be assuming that we do not know the variance, and so we'll be calculating that pooled variance. And the whole idea here is that we're going to be trying to test whether two means are equal. And all this that I wrote down, that applies whether we have this alternative hypothesis that the two means are not equal. It could apply whether we have this alternative hypothesis that mu x is less than mu y, or we can use all of these calculations under this alternative hypothesis that mu x is less than mu y. So far, we've talked about hypothesis testing for one mean when sigma squared was known, one mean when sigma squared was unknown, and two means when sigma squared was unknown. And also we touched a little bit on two means when sigma squared was known. Now we're going to start talking about proportion. So we're still doing hypothesis testing. Now we're going to focus on a proportion rather than a mean. All right, so what's our setup for the proportions? All right, suppose that we have a random variable y. It has a binomial distribution with n trials and probability of success p. So n is known. In other words, we know how many times we flip the coin, but p is unknown. We don't know the probability of heads or tails. Okay, so we want to test p. So for example, say you like eating M&Ms and you eat a lot of them and you notice it seems like there are more red M&Ms than the factory claims. So just making this up, maybe the factory that produces M&Ms claims that 10% of M&Ms are red. You think more than 10% of M&Ms are red. So you want to test the M&M factory's claim. So your null hypothesis is going to be what the M&M factory claims, which is p equals 0.1, where p is the probability of a red M&M. And then the alternative is going to be what you think, which is p is greater than 0.1. All right, so we're trying to figure something out about p, so it would make sense to look at the sample proportion. The sample proportion is just the number of red M&Ms divided by the number of M&Ms that you sample. So y over n is going to be our estimator for p. Usually we call that p hat, but we can write it y over n just to be explicit about it. All right, so we have an estimator for p. We need to know the distribution of y over n. So in other words, if we take a sample of n M&Ms and calculate p hat for it, and then do that again, another sample of n M&Ms, calculate p hat for it, and then again and again, how much is that sample proportion going to vary, and what's its distribution? All right, so the distribution of our sample proportion is approximately normal with mean p and then variance. Actually, this is the standard deviation, the square root of p times 1 minus p over n. All right. So under the null hypothesis, under the claim that p equals 0.1, we can rewrite this and substitute out the p's with 0.1. So then our sample proportion is going to be approximately normally distributed with mean 0.1 and then standard error square root of 0.1 times 1 minus 0.1 divided by the sample size n. So here it is for our M&M example, and then up here it's more generally written. So the sample proportion is approximately normally distributed with mean given by the null hypothesis, and then the standard error is also given by the null hypothesis. All right, so if we want to test the null hypothesis that a proportion is equal to some value p naught, we're going to use this test statistic, sample proportion minus the value of the proportion under the null hypothesis divided by the standard error under the null hypothesis. So remember, we calculate our test statistic under the null hypothesis, and then we use the approximate sampling distribution standard normal, because that's what's given here. All right, so summary, if you're looking to test one proportion, we're going to use the estimator y over n, and we know that y over n has approximately this distribution under the null hypothesis, normal, mean p naught, which is the value of p under the null hypothesis, and then the standard error under the null hypothesis. So we can rewrite this. So here's our test statistic, and then we know that under the null hypothesis is going to have a distribution that's standard normal.